Hey YouTube, it's Dimitri, and today we're going to talk about Zillow, the whole debacle of them being stuck with a bunch of houses and then now trying to get rid of them. And of course, they're going to be selling them at losses because they paid way too much given their iBuyer kind of model process here. So they failed on a bunch of statistical modeling methodologies here. Again, statistical modeling includes data science, machine learning, and all that in the realm of when I talk. We will talk about a lot of issues though from a pure data perspective in this video. Again, I don't really know. I don't think anybody knows, at least not publicly, what's going on with Zillow on their actual failures. But we're going to dive in here in a little bit of detail on some time series. I'll put a link above or below. I attempted to do this video, and I tried to talk about this from a technical perspective in the sense that I'm trying to teach and explain and talk. And I can't get into enough detail really because I really need like 100 plus hours of teaching. And even after doing that, even after training, professional colleagues who do this for a living, it takes me more than 5 years to kind of just barely get the ideas into people's heads. So anyways, let's just dive on in here. And first off, I want to thank Olga here. So she donated $3 through my Ko-Fi, which I'll put a link below. She bought me tea today. We are drinking decaf black tea because it is like 9 p.m. at night as I'm shooting this. But anyways, a big thank you for her, a big shout out. If you want to give back to the channel, feel free to use the link below and you can donate $3 to help support this channel. Okay, so first off, why am I even qualified to talk about this? Why am I talking about this? So one, Billy, subscriber, asked me to talk about this. Two, though, I work in model validation in the banking industry. The banking industry is probably one of the most, if not the most, regulated industries, especially when it comes to modeling and statistical data science, machine learning, methodology, and practices. Tech, on the other hand, so this is what I would consider Zillow to be. The tech realm is very unregulated. There's not a lot of standards. There's not a lot of rigor inside of the way they do things. It's kind of like, just rush through and break things and see if we can come up with great discoveries. And that's fine and dandy, but that's not the best way to go about things when money is involved. So I actually get paid professionally to go in and look at these sorts of models. I've worked in model development, which is the people that actually build these sorts of models. So I could be in the same seat as those Zillow people, but at a bank building very, very similar models. But I work also in validation, which is the second half of this, which is I actually look at these models that someone builds and I professionally go in and critique them and tear them apart and explain why they do or don't work. And time series happens to be my expertise here. So this is where it's coming in at. This is why I'm somewhat of an expert on this topic. To add a little more flavor to this as well, I've worked in valuations both in mortgage and auto. So this is going to be all specific to mortgage here, real estate properties and valuations. So yes, I've actually built models and validated models related to real estate and exactly similar problems to this. I've actually modeled assets on book for banks where basically they get stuck with a bunch of properties they can't sell back in the 2007, 2008 financial crisis due to the housing bubble. So almost the same scenario here, far worse, torn these models apart, looked at the ins and outs, but we're going to dive in here from a technical perspective, keeping very high level. I'll mention, I'll put like a link below or above or whatever in the description or in the top here of another video I attempted to do this. I don't want to cover too many crazy details because it can get very deep. And just to give you a base understanding of like what you would even need to start grasping these at a professional level, you would need a bunch of textbooks, which I have. So this is like a probability and statistics textbook. This is not the only one I have. I have a stack of other ones from undergrad, for example, from engineering schools, from math departments, just books that you would need in general. You would also need something like this, which is a really, really thick book. This is an econometrics book. This is specializing in time series applications, the back half of it, but it also specializes in cross-sectional data, which we'll talk about here in a second, and panel data models, which we'll also talk about. And then if you really want to get into the meats of these things and a mathematical, rigorous understanding of really what's going on and why these things are failing, and again, these things fail all the time in banks, so don't get me wrong, this isn't like a tech-only problem. This is a 99.9% of people doing statistical modeling and time series or machine learning and time series are just wrong. But you would need more books like this. I have another book as well. This is Introduction to Stochastic Calculus with Applications. I have another entire book just on stochastic processes as well. Again, please note, none of these books, including this last one, are finance related at all. So this is another great book, extremely thick. This is Time Series Analysis by Hamilton. This is probably one of the best books, but again, you need a math background to really do this and understand this. Plus, you need all those other books on top of it as well to really grasp what's going on here. So to start off with here, the first point I want to make is this is not an easy problem to solve. Okay, you don't run out and get some sort of package and you just program in here, like using profit as everyone's kind of pointing at and making fun of Zillow on. You don't just run out and point things out and just do that. The second point I want to make here as well, so I work in a bank. All large banks that are doing time series modeling, especially on a serious level, are going to be using SAS. They're not going to be using Python. They're not going to be using R. They're going to be using SAS because it's easy to train people. It's extremely expensive, but it does it correctly. And I'll point out, too, the Engel-Granger methodology, along with the Dickey-Fuller test for doing time series modeling and structuring and all this. SAS actually paid David Dickey to come in and actually help them build, basically the world's best time series tool out there. So it's the best. Now, that being said, there are other firms that do use Python and R and do it correctly. However, these firms, typically like hedge funds, for example, I'm hoping technology firms, but it doesn't seem like it, they have people actually writing custom packages that are only available to those firms that are actually done correctly. It's quite similar to SAS and have a lot of other functionalities that, quite frankly, you just can't get in R and Python from just the basics. You need to program these things out. And again, to do that, you need a whole stack of other textbooks and expertise in optimization and programming and computer science, as well as the math and stats theory that goes in behind this with probability to be able to calculate these things. So this is all going to kind of pile in here. But without too much other rambling and discussion of why this is a challenging problem, let's dive into the technical components here. Okay, so first off here, we're going to cover data structure and defining the problem. And this is going to be a whole issue in itself, which I think is going to apply to the Zillow case. Two, we're going to cover stationarity. And if you know me at all, you follow this channel, I beat stationarity home because it is such a complex topic within itself. I could probably create an entire university course, like an entire semester just on stationarity. And to be honest, I could probably create multiple classes on this coming from all these different angles of probability theory, math, specifically for finance, of course, what we're talking about, machine learning applications as well, and data science and how this all plays together. But I will make an attempt to kind of cover a little bit of that and talk about why that's important. And then finally here, we're going to talk about something that we call performance monitoring. And I'm going to note here as well, this is going to be, metrics. So this is like what we typically think about. But more importantly, this is going to be assumptions, okay? And to really dive in here, so let's just start off here with data, structure, and more specifically, this is going to be relevant to the problem here. So one of the problems when you model things that are asset valued that depreciate based on usage, I mean like human usage here, like very differently, it's hard to model. And what I mean by this is, say you have, two houses here, they got a little door, they have a window, I don't know. Anyways, you have this house and you have another house over here. And these houses are the exact same and they have some nice window in it. The issue that you come down to is, how are these houses actually maintained and treated? So one of the main key issues here that we're going to talk about is you're going to have issues with maintenance here or usage. So I don't know, put usage, maintenance, I don't know, something like this. These are going to be things that impact it negatively that you can't really measure. So these are going to be non-measurable. And again, there are tricky ways to measure these. I don't know how ethical they are. The other thing here, so I'll uncross this real quick. The second piece is going to be the fact that you have, house specific data that does not change here. So this is going to be, like, I don't know, 1,200 square feet, at this one, and this one's going to have the same, 1,200 square feet. But then also you need to consider things specific to the house. For example, which state or region of the United States is this in? Again, you could use something like zip code. You can use things, for example, like how many car garages do you have? You could use all kinds of things. These are house-specific data here. And then also the final most challenging piece here that we're going to have is that we're going to have market conditions here. So market conditions are going to be one of the main drivers of what screwed over Zillow from my, perspective on this. This is really economic modeling, and more specifically, we call this econometrics. And what this is really doing is just basically using time series and economic factors, for example, like GDP, unemployment, I don't know how well the stock market's doing, these sort of things to actually impact this. And why this is important is because, let's say unemployment rate is one of those examples here. When unemployment goes really, really high, people aren't making money, they can't afford to pay their bills, they can't afford their houses, they get evicted. And then a lot of times we have a lot of houses on the market because there's not a demand for houses anymore, right? People can't afford them, they're getting out of their current houses, they're probably moving into apartments, or they're going homeless or some sort of scenario here. And then, and the other flip side of this, if unemployment goes down really, really far, the economy's booming, so GDP is up, all these things are kind of moving in the right direction. We see the housing market boom. Right now, I would say we're in a zombie state economically where the federal government in the United States is just pumping in all these fake dollars, trying to keep GDP high, trying to keep unemployment low, which is not working. Again, inflation now is going through the roof. We're kind of grappling with this, struggling with this problem here a bit. Just because of poor economic policy, but I'm not going to get too much into that. And so when you have this problem here, right, we're going to have really these two kind of things we're going to focus on, which is going to be house specific, which is going to be these first two components, and then we're going to have the macroeconomic one. Now, the problem with this on the scale and the functionality of how you actually model this is I want to model this out at a very specific level. So for each and every house, I want a very unique price here. But the issue that you end up with is that you have some sort of price here. So we'll call this the house price, and we'll call this, time. And I don't know, we'd have this, let's say like monthly data, and you'd have, I don't know, let's just say this is 2018 for simplicity, and this is, I don't know, 2020. So of course this would be like January right here or something, I don't know. Anyways, you'd have enough tick marks on the bottom to have some sort of house pricing, and you'd like to have something that looks like this so that you can predict this, okay? So this is gonna be a perfect time series in itself. Now, the issue with this is that typically we don't have that. We have, for example, this house sold in 2018 here, and then it resold, let's say, in, I don't know, the end of 2019 here, and then it's going to be sold at this point, and the question is, what is the valuation on this? Well, we would not actually see all of this pink in the middle, right, which would be the historic real valuation of this house. We have to actually model this. But the problem is when you only have, two data points, there's not a lot you can model here. So you kind of just throw time series out a lot of times and say, okay, screw time series. This makes no sense. What I'm really going to look at is I'm going to look at the house-specific variables here. And we're going to build a cross-sectional model. So one terrible approach is just using cross-sectional. This is really where you just assume there's no time dependency. You're just going to model this. I see this mistake constantly in people in the finance industry and other tech industries doing this. But you would build some sort of model such that, now again, I understand you can use machine learning and decision trees and gradient boosting and neural networks to do this. But we're going to use basic math and stats here just to get the ideas through our heads. We would have house price, and we would have, something such that you would have like a beta 1 on this variable called square footage. And then you'd have, like beta 2 based on like, I don't know, some sort of value such as, number of baths, number of bedrooms, all that stuff. And you'd have all these out to, I don't know, beta n, variable x of n, and you'd have some sort of epsilon. Now, the problem with this is it's not going to pick up a lot of times this drift. So we're seeing a drift here, or in time series, right, you might see like a jump. So you have this little bit of a jump, and then we see kind of a drawback, and then we see another kind of a jump, and then a drawback. And these can be based on market conditions. These can be based on unemployment reports that come out. These can be based on a lot of things. Trying to capture this is extremely hard. And the biggest issue with this, which I try to explain, but I fail miserably at explaining this to most people. Now we're going to get into the time series and stationarity here a little bit. So I'm bouncing between the ideas here, but for stationarity, what ends up happening is you end up with some sort of thing like this, where it's house price, and you have, I don't know, we'll do square footage, and you have some sort of data like this. And then the issue is that when you run this regression, the slope of this, so the slope of this line here is going to be your beta coefficient. So we'll call it beta 1. And let's just say, I don't know, it's something like 0.31. I'm just making this up. Now, the issue is when you have time, so when you have this time and it looks like this, and it looks something like you have some sort of time here. Now, the issue is when you take the relationship from here to here, it holds, and beta 1 is equal to 0.31. Now, when data is not stationary, what happens is these beta coefficients are no longer reliable, and they shift with time because this relationship actually changes. So now what happens is this actually becomes, house price here, square footage, the exact same variable. Let's say that we used here, this is like 2018 data, and then over here we're going to use like 2019 data. The dots, if you're lucky, have the same directional relationship here, but they end up flattening out. So now in this example, our beta 1 might end up being like 0.22, right? Which doesn't seem like a lot, but when you start valuing houses, this can make a massive impact on the model. So then you have a beta 2 here, which is 0.22. And then if you look here in this example here, again, this is something crucial. When we start having a downward trend, when we resample and we end up going into 2020, what we end up with might be something that's now flattened to the point that it's actually become negative, and now beta 1 is now like 0.01. It's a negative 0.01, so you have this slope, and beta, so this is technically beta 1. This is the same beta. Beta 1 is equal to negative 0.01. So these relationships are changing, and there's no way to fix this, and people throw their hands up and they say, time series sucks, I don't like all this. I'm just going to keep throwing all this data together, and I'm going to build a model, and I'm going to throw all this data in this, and so I'm going to create some sort of model now. It's 2018 through 2020, and the slope here is fairly flat, but we have some sort of relationship, and beta 1, the true value, put in air quotes, the true value is going to be something like 0.15. But you see the issue though is we add data in time, these relationships don't hold, right? You might have the same direction, but now the model's deteriorating in very short periods because time series is kind of impacting that. So we need to fix that. And there are a couple ways to do this and a couple issues that we're going to talk about here. But okay, so before I get going too far into the stationarity issue here, let's just wrap up point 1. And this is going to be the issue, which is for a time series, we need a lot of data, okay? A lot of data. And when I say this, we need a lot of data on each house, okay? If we want to predict each house value very uniquely, very precise, which is what data science, machine learning people try to do a lot. That's what the tech industry tries to do too much. They overfit things because they do this. We just don't have the data, though, to even do this correctly. So you could use a fancy machine learning model, but we don't really have the data to do that because data is sparse. The other issue that's going to be here is that we can't really use cross-sectional because there are time dependencies. And these time dependencies are going to create issues, and we're going to talk about stationarity. And we're going to talk about, which we've already talked a little bit about stationarity, but we're going to also talk about serial correlation, okay? And these two issues within themselves are actually related, but this is why we can't use a cross-sectional model. And I've seen people attempt to take like GDP and say, okay, we're going to take GDP and we're going to throw it into this model, and we're going to pretend it's cross-sectional, and everybody gets the same GDP value if they were sampled in one period. And then we're going to, so it's kind of like pooled OLS if you want to think of it that way, which is a panel model. But now the issue is we can't really do computer or cross-sectional regression here. And as I mentioned, we're going to talk about panel regression or panel data. You can call it either one. Pooled OLS is a common approach for this. But again, what it expects here is that we have unique values like houses, and we have both cross-sectional and time series together. So we would have, I call them threads, but time series of values here. You would have like a bunch of threads, such as like, this is like house 1, and then you would have, like a house 2, which is kind of similar in the same area, and this is house 2, and then you would have, all the way out to like house n, which, n could be equal to like, 1,000 houses or plus. But the issue here is we don't have these threads. These charts only look like something like this, where I have a dot here and a dot here where this one sold, and then this house sold here, and then like here. And so you can't use, panel regression or panel data, panel models here to do this. So what do? We just throw our hands up and say, screw it, we're not going to do it? No. What we're going to do here is we're going to have to aggregate the data. And so we're still going to get one prediction per house per month, okay? Or per day or per whatever you're trying to get this to here. But what we're going to do is we're going to start aggregating and treating a lot of these houses as the same. Now, this is a challenging issue in itself, and you have to kind of really work with this. But the ways to do this is, one way to do this is trying to group houses. And so we can do grouping. We call it stratification. There's another terminology for this, another methodology. You can also do it cluster algorithms and things like that. But what you want to do is try to get as many houses together as possible. And why this is important is now we're going to have, this house one sold here, house two. So house one sold in 2 spots. So this is time. And this is the house pricing. And then you're going to have another house, as we mentioned, that sold like here and one that sold here. And if we have a bunch of tick marks across this, what you're going to hopefully get is a bunch of these houses. So this is like house 1, house 2. You'd have a bunch of different houses such that you would end up with a bunch of dots, at different points. Now, of course, they wouldn't all be green. They'd be different colors for different houses. But then a lot of times you can even take cross-sectional. So you have a couple values in these areas. So let's say you have a couple here and a couple here and a couple here. And what you're going to end up doing is averaging each one of these time periods on houses based on specific group or segmentation or stratification here. Now, you need to be extremely careful in how you do this, and this is one reason their model could have failed if they didn't stratify correctly, or they didn't use the right variables, or they didn't keep an eye on this, because this is going to be, as I'm going to tell you here, this is an assumption. Okay, so keep an eye out for all these assumptions we're making. But you're going to average all these up, and what this is end up going to do for you is you're going to end up with some sort of plot such that it looks like what we've been talking about. And this would be like, 2020, and this would be like 2018, or more specifically, this should really go to like, 2000, something longer. So you have a nice horizon and relationship development process here with a lot of data. But you're going to have to aggregate this data to the point that you can do this. Now, you can still get a prediction for an individual house, and you can have varying components in these models such that you have like square footage, number of bedrooms, number of bathrooms, all those house specific variables. But then you need to incorporate at the same time these sorts of modeling structures and frameworks. We're going to try to add in here at the same time, we're going to add in macroeconomic factors from the economy. Okay. Now, I've done a whole methodology on this before. It's fairly complicated to do this and do this correctly. But if you do this right, you can actually end up building a time series model that works quite well. Okay, so I hope the takeaway here is you realize we have to figure out how to get our data structured correctly. You can't just take all these housing prices, throw them into some sort of regression, which I pray, fingers crossed, they didn't do this, or I pray that they did the assumptions correctly and did some stratification and made actual pure time series off of these, but also realizing they're going to have to monitor these assumptions here, which we'll talk about at the end. And if they model them correctly, we can make sure these aren't breaking down, and if they are, you can refit and adjust. So this is the first issue with the data structure and defining the problem correctly. Okay, so here we're going to talk about stationarity. And we're going to talk about this quickly, but one thing we mentioned earlier, so point A was that the coefficients change with time. Now, of course, any sort of regression, when you add new data, the coefficients are going to change. But what we're looking for here is that we want a stable relationship. And if these are not stable, they're not predictable. And by definition, stationarity, realistically, in simple people terms, just means stability, or more appropriately, it means predictability. So let me just make the statement that's going to crush all these data scientists out there because for some reason there's delusional thoughts, as well as econometricians and statisticians that don't really understand time series. There is no such model as a non-stationary model. Okay, and everyone's going to jump in the comments and say error correction models. Okay, well, they actually require stationarity and co-integration, and co-integration is a form of stationarity, but more strict. And that's a whole other video. And not to mention, people have books out there on machine learning where it's not stationary and it magically does things. Yeah, these things don't exist. These things don't exist in statistics. They don't exist in data science or machine learning. It doesn't exist. You have to have some sort of predictability. And so the other point I wanted to talk about just with stationarity and why this is important and why the coefficients change and why this is so impactful is that the way that we view probability theory is you view some sort of pooling, right? We used to call this like the sample space. I think they normally call it like R. Anyways, your sample space is all possible values of homes. Now, I'm not going to get into theoretical constructs here on this because I believe home prices can actually be negative, but that's a whole other video. But typically we like to think, that the possibility for ranges of home prices is going to be $0. And I'm going to say really like infinity, but I think like the max value homes have sold for are like 100 million. I know there's one in New York that's 100 million. You could have crazy things like, I don't know, some castles in Europe that might be, I don't know, like billions of dollars. So we could get into the billions. But there's going to be some sort of sample space here, and you're going to have all these data points of possible house prices. Now, the way we think about stochastic processes, which are time series here, is that we randomly sample from this pool here. But when we model this pool, we end up with something, so some sort of distribution. And if you know anything about histograms, right, we think that things are typically what we call a normal, and it looks something like this, okay? And you have some sort of normality here. Now, of course, for house pricing, this is not how it actually works, right? Because as we just talked about, we're going to go from 0 to infinity, and realistically, this distribution is going to be something that's like this, where you have like this price, like this tail is technically going on forever for infinity. There's a possibility you have a house, let's say like out here's the billions, and then, this is going to be like 100 million. But you're going to have most of your data in some sort of range in here. And, house pricing in here might be, I don't know, let's say like, I don't know. Right now the housing market's just ridiculous. So I'm just going to say $500,000, but realistically this is probably more like $300,000, so 300K. And then you'd have houses all the way down here, all the way to $0. Let's say some shambled, burnt down shack in Detroit or something. So this is going to be a non-symmetrical distribution. Here's this is non-symmetrical. Now, for math purposes, for other purposes, for stationarity, for example, we like to have something symmetrical. So we want to get something that looks like this. The easiest way to do this is often to do a differencing. So if you had a time series like this, you would take, this is time t, and this is time, t minus 1. So we'll say house price, which is, difference here as delta, is going to be house price of t minus house price of t minus 1. Now, this is just going to be the dollar change in value from each time period. And so, we'd expect these to be somewhat like this normal distribution where you have 0 and it can go either positive or negative and you have nice symmetrical distribution. Now, we also like to think in probability theory as we randomly sample. So the way a time series or a stochastic processes works is we randomly sample from here and we pull out data point 1. We randomly sample again, and we pull out data point 2. Now, this chart here is going to apply to this raw chart, but when we actually end up doing some sort of chart across time here, the growth rates are going to bounce somewhere around 0, as we pointed out, and they'll look something like this. And if you zoom in on them, there are actual seasonal and cyclical patterns based on housing markets and bubbles and booms and economic factors, and all these are going to play into this. But the most important thing to realize here is that we're working with distributions, and stationarity or weak stationarity, so I'll write it out, is where you have a constant mean, which is going to be mu, and you have a constant variance or standard deviation, squared here. Anyways, the variance is going to be constant across time as well. And so we need to have a stable prediction, because if it's stable, we can predict it. If it's not stable, we can't predict it. There's no way to do it. Now, again, all those textbooks I showed you at the beginning, the stochastic calculus, the time series, the probability theories, you need all of that to fully grasp this. And I could go into all kinds of nuanced details around this. But just trust me, you have to have stationarity in everything inside the model to do this. And to debunk one more myth I've seen online on somebody else talking about the Zillow's case here, we're going to talk about levels of integration. So as I mentioned before, right, if you have a house price and it's the delta, so it's house price t minus house price of t minus 1, this is called integration of level 1. Okay. Now you can have an integration of level 2 where you end up differencing it a second time. And you can difference it a third time and a fourth time and a fifth time. And technically something that is not differenced, so like h house price of time t, this is going to be called integration level 0. There's zero differencing that occurs here, right? So this is important. Not all time series in finance are I1, and this is what I've seen people randomly claim, and then they start going on to some tangent about Brownian motion. And yes, Brownian motion, is going to have specific properties of normality. You can get a normal distribution out of it, and you can actually get stationarity. And this is extremely important for derivative pricing. However, you actually have to test every single time series stochastic processes that you have. And some, including HPI, so house pricing index, sometimes it's just not stationary. So we need to do very tricky things. So we can do something called seasonal differencing, which for some reason they just don't teach in schools anymore. I don't know why. This is actually really common. Seasonal differencing. In other books, they have fractional differencing, which I'm not a fan of for conceptual reasons and how it actually practically works. And anyways, you can do all kinds of things that make this differenceable. Sometimes, though, I've seen HPI, depending on what market you're looking at. So again, you can have the United States, you can have regional, and you can have statewide. You can look at this in other countries. Sometimes it's actually going to be an I2 process. So don't ever assume anything is I1, I2, or whatever, and you just go in and different things blindly. You actually need to do what is called an augmented Dickey-Fuller test, which is a test for stationarity. As I mentioned, the reason SAS is so good at time series is because, yes, Dickey himself helped SAS do this from my understanding, what they've told me. So you need to test this. And then I'll point out a few things here too. There's going to be something called rho, and then there's the p-value of rho. There's going to be something called tau, and then there's a p-value of tau. This test is read wrong like 99.9% of times, and I don't know why. You can literally go back and read the original paper from Dickey and Fuller on this. You're going to have numbers here, and they're typically negative. So I don't know, negative 100, negative 10, I don't know. Maybe it's like 0.5. And then in these cases, when rho is less than 1, you use the p-values for rho, okay? When rho is going to be greater than 1 or equal to 1 here, we're going to use the p-values for tau. Okay, now there's going to be other values here, and there's going to be p-values over here. So typically what you'll see, if this is done correctly, and again, R in Python, I've seen packages that have this, but they don't typically implement them correctly, and I noticed that rho and tau end up matching values for some reason, which isn't supposed to be happening. You'll have something like 0.001, 0.0235, and then, this negative 10 is going to be like 0.015. And then when you get to something such as like, I don't know, 115 or something, some value for rho, we end up with this is going to be 0.9999. And so people say, oh, it fails at lag 5. It's not stationary across time, at least not at lag 5. But then if you use your actual brain here and look over here, it's typically something like this, okay? So reading the test is important as well. I'm guessing this is going to be another key issue and something that could have gone wrong with Zillow. And then finally here to wrap up this whole video, we're going to talk about the third point, and this is going to be, performance monitoring, and more specifically, more importantly, just monitoring in general, because typically what I see people talk about a lot in finance and banking and other industries as well, is they say, okay, we are going to monitor something like your MAPE, or we're going to monitor something like your MPE, or your mean squared error. And they're going to have some rule here, like if this goes, so you have thresholds here. Like, okay, so we say we're good, we'll call it green. We'll have amber, which is basically yellow. And then we'll have red. Okay, and for these thresholds, I'll have something like, I don't know. So say the maximum value is 1, so 1.00. And they'll say this goes down to like 0.85. And then they'll say, okay, 0.85 goes down to, I don't know, 0.5. And then from 0.5 down to 0, we have a red amber warning sign here. Now, this is fine and this works. And you could say this is for like, I don't know, we'll call this like our MAPE here, right? So let's just assume we have between 0 and 1 for fit, some sort of metric. And this is good, and this is fine, and this works dandy. We're now missing the key piece here, which I'm going to talk about, and even banks are missing this, so this isn't anything like crazily out of there. We don't have a lot of assumptions, okay? And what I mean by this is we are not monitoring the assumptions. So when we talked about earlier, there were going to be different assumptions. For example, like there's an assumption on how you structure your data. There's going to be an assumption here on the variable selection process here, okay? So variable selection. There's going to be all kinds of assumptions baked into how you structure your data, how you fit your model, the model structure you chose, why you chose the model structure. And I didn't talk a lot about serial correlation, but basically the concept of serial correlation is that when you have this time series and it's being randomly sampled, each period is going to be very close to each other. So point A is close to point B is close to point C. Houses, economic, finance data is all serially correlated. So therefore you have to use time series. You can't use cross-sectional to do this. And what ends up happening here is that, right, your house doesn't change value significantly over time. Like if you say my house is worth like $300,000 today, tomorrow you come back, it's going to be $300,000, right? I mean, maybe it's, I don't know, $299,950. Maybe I broke something in my house and it's $50 less in value. But realistically, it's going to be close to that, and it's going to slowly depreciate across time. Is that serial correlation is one of these important factors and things to monitor and look at and check the relationships here. Now, again, we have all these assumptions we talked about. We also need to check the relationships. So when you build time series models, serial correlation comes in the form that typically you have something that's lagged. So, I mean, you have like y of t is equal to, alpha, so some intercept term, plus beta 1, and then times some variable here, but it could be yt minus 1, and this is considered an auto-regressive term. And this is really, really amazing for time series and how it works, because what you do is say, okay, I'm going to take the value of the house of the last period that we have. So let's say the house is $300,000, and we're going to look at all the different factors and variables that impact this. Now, the base value of that house isn't going to change. The house-specific variables do not change, right? The square footage doesn't change, but technically, I guess it could if you expanded the house or something, but really, it doesn't really change. So you say, okay, the value is almost the exact same as yesterday or the last period here. And then when the thing that's driving it and changing is going to be the macroeconomic factors like unemployment, GDP, maybe even things such as supply and demand in a zip code, in a neighborhood, in a city, in a state, those sorts of things. Now, those are going to change across time. Those are serially correlated. And then you need to make sure you have stationarity to make sure the relationships are true and not spurious. You're not maximizing correlation, which is basically what data science and machine learning does. You need to go in and look at this and try to figure out if these are true, honest, real relationships, okay? And you need to monitor all these kind of components. And so when you go back into some sort of testing process here, right, these sorts of things need to be monitored and tested. And there's a variety of ways of doing this. Refitting models, checking model fits. Again, monitoring these errors, which I'm guessing Zillow is already doing, right? I'm going to assume that. But if they're not, I mean, they also need to be checking down here at the assumptions and figuring out like, okay, we went from green, like at 0.99, we're getting now to like 0.88. We're monitoring again, it's at 0.85. We're still kind of good. And then it's at, slowly moving. These are things to look at because they can help you then dive back into the assumptions, figure out if you need to refit the model. The other issue is, guess what? You need to have stress testing periods and figure out how much risk you're taking in different portfolios, diversification, so finance theory here. Now, I don't know on Zillow's methodology and how they spread their risk, but again, the market can crash, and if the market crashes, for example, the United States crashes, all markets are impacted by this and everyone's going to be losing value. So all things to consider, all things that are very, very important to why Zillow could have failed due to some of these reasons in the modeling realm. So anyways, these are kind of my points here, right? Data structure, defining the problems. 2 is going to be stationarity and time series. 3 is going to be monitoring performance. And then finally, the last kind of point here is that these models are extremely hard to build here. And I hope you realize that as I've pointed things out, like how do you structure your data, the assumptions and decisions you have to make along the way, these sorts of issues like getting stationarity. Often you can't find stationarity. How do you get it as close to stationary as possible? How do you monitor that then? Because you have this massive risk where it's not predictable and it could jump at any moment. Again, these are very real world problems. You don't just throw things into packages, things come out and you build models. A lot of thought, a lot of intelligence, a lot of additional testing, which we don't see in a lot of textbooks, for example. All this additional testing needs to be taught and understood around these models so they can be properly monitored. But more importantly, the reason it probably failed is it's hard, okay? It's just a really hard problem to model, no matter how skilled you are. But the sad reality is most people in the quantitative finance realm, in the data science and machine learning realm, in the analytics realm, aren't experts on time series. It is one of the very niche areas. It is extremely hard to master and requires a lot of depth in different areas to fully grasp it. So my guess is all these issues kind of compiling up together in the sense that, right, it's hard to model. I'm guessing a lot of these things weren't in place. I would almost guarantee probably the number one cause of failed statistical models everywhere, including probably Zillow, again, I don't know, is issues with stationarity. So those are my 2 cents. Anyways, thank you guys for watching. Don't forget to like, share, and subscribe. And as always, until next time.